Hello and welcome to today's session. In this session, we will focus on learning outcome 2, understand database design. Have you ever wondered how data is stored in a way that is both efficient and secure? Today, we will explore the fascinating world of database design, uncovering the processes that ensure data is organized, accessible, and well protected. From requirements analysis to conceptual, logical, and physical design, we will examine each stage and understand how they contribute to optimal data management. By the end of this session, you will gain a clear understanding of how thoughtful database design supports effective decision-making and smooth organizational operations. Requirements analysis is the first step in database design. It involves understanding the data needs of users and business processes. Key activities include gathering information from stakeholders and identifying data elements. The output is a comprehensive requirements document. This document outlines what the database should achieve. Conceptual design creates a high-level model of data requirements. It doesn't consider physical implementation. Entity relationship diagrams are developed to represent entities and relationships. The output includes diagrams and a conceptual schema. This schema visually represents the database structure. Logical design translates the conceptual model into a logical structure. This structure can be implemented in a database management system. Activities include normalizing data and defining tables and keys. The output is a logical schema with detailed table structures. It includes primary and foreign keys and integrity constraints. Physical design turns the logical structure into a physical one. This structure is stored in the database management system. Activities include determining storage structures and indexing strategies. The output is a physical schema outlining data storage and management. This ensures optimal performance and data access. Entities are objects in the database distinguishable from others. Examples include customers, products, and orders. Attributes are characteristics of entities, like a customer's name or address. Understanding these concepts helps in structuring data effectively. They form the foundation of database design. Relationships define how entities interact. Types include one-to-one, one-to-many, and many-to-many. For example, a customer places many orders, a one-to-many relationship. Understanding relationships is crucial for data organization. They ensure data is structured hierarchically. Keys are essential for database integrity. A primary key uniquely identifies each record in a table. A foreign key creates a link between two tables. It ensures referential integrity by referencing a primary key. Keys are vital for maintaining data accuracy. Normalization reduces data redundancy and improves integrity. It involves structuring the database to minimize redundancy. Normal forms guide this process, like first, second, and third normal forms. Each form has specific requirements and benefits. Normalization ensures efficient and reliable data storage. Indexing speeds up data retrieval operations. Types include primary, secondary, and composite indexes. Proper indexing enhances query performance. It allows faster data access, crucial for large databases. Indexing is a key aspect of physical database design. Data integrity ensures accuracy and consistency within the database. Types include entity, referential, and domain integrity. These principles maintain data validity and reliability. Integrity constraints enforce these rules, preventing data corruption. Ensuring data integrity is essential for database reliability. Database administration ensures efficient and secure database operation. It involves tasks like maintaining data integrity and security. The ACID principles play a crucial role in transaction reliability. Administrators implement integrity checks and security controls. These practices safeguard data and ensure smooth operation. ACID principles guarantee reliable transaction processing. Atomicity ensures all operations in a transaction are completed or none. Consistency maintains valid database states. Isolation ensures transactions do not interfere with each other. Durability ensures committed transactions persist despite failures. Integrity constraints ensure data accuracy and consistency. Referential integrity maintains logical consistency between tables. Domain integrity enforces valid data entry according to rules. Entity integrity ensures unique identification of records. Foreign key integrity ensures correct referencing between tables. A database schema defines the logical structure of a database. It includes tables, fields, relationships, and constraints. Schemas specify how data is organized and managed. They are crucial for understanding database architecture. A well-designed schema ensures efficient data management. A database administrator manages and maintains database systems. Responsibilities include installation, configuration, and performance tuning. DBAs ensure data integrity, security, and user management. They develop backup strategies and troubleshoot issues. Their role is vital for database performance and security. DBAs need skills in database design and performance tuning. They manage security, backup, and recovery processes. User management and troubleshooting are key responsibilities. DBAs document configurations and generate reports. Their expertise ensures reliable and secure database operations. Conclusion: understanding database design and administration is essential for effective data management. Each stage, from initial design to ongoing administration, plays a critical role in maintaining data integrity, security, and scalability. Mastery of these concepts enables the creation of robust databases that support organizational data requirements and facilitate sustainable growth. Any questions or concerns? Send a WhatsApp message to 074843 61688 and our team will gladly assist. Thank you, and see you next time.